So we are looking at the momentum equation. Now this equation is one equation we use for analyzing fluid flow and for discovering the resultant force acting on a fluid when it is going through some section which is bent, for example, maybe a pipe or a cross section of that nature. Now, what is beautiful about it is that it applies Newton's second law of motion. Now, how that works out is what we'll look at soon. Now, so according to this equation, the net force acting on a mass of fluid is equal to the change in momentum of fluid per unit time in that direction. Because if you look at Newton's second law, it respects direction. So that is what this equation, as you put up a statement, also brings out. Now we are saying, according to the equation, it's F equals ma. So from there, we're saying F is the force, m is the mass, a the acceleration, represented by dv dt. So meaning that you can now put this back in the equation where there's a, you put dv dt. When you do that, this is what you have, m dv dt. Then after that, you also have just rearranging this information to make sure you can have d mv dt. Then we can now go ahead and rewrite. We just cross multiply. So on the left-hand side, this expression we're having here, this is our impulse. Impulse is a product of force and time. Then on the right-hand side, this is our change in momentum. Rather, that's our momentum showing there. Of course, we're saying that we apply this, like I mentioned in the introduction. This is where we apply it when we're trying to look at the resultant force on a fluid flow system, which is going through perhaps a pipe section, which is bending, something like this. So we have section 1 and section 2. Fluid which was here between 1 and 1 to 1 dash or 1 to going to 1 dash 2 dash, that volume there, you can call it volume 1 or the discharge through there, including section 2 trapped by 3, 4, and 3 dash 4 dash between the solid line and the dotted lines. The displacement or the distance covered there, the displacement is simply the ds2, there ds1, that's the distance, meaning that if you're talking about the volume, it's going to be the cross-section area multiplied by this displacement ds1. So meaning, if you go back now to this, we know that density is mass per unit volume. So if I'm looking for mass, I should multiply density times volume. So here, what you see is this. I already have density. Density is here. Then the volume is this product of cross-section area by that displacement. So this gives me mass 1. For mass 2, it's the same thing, density 2 times this product of area 2 and displacement 2. So what I have here now is basically the same fluid mass for, this is the fluid mass for this section, which is 4, 3, 3 dash, 4 dash trapped in there. The first one for section 1 is that fluid mass there, which is 1, 2, and 2 dash 1 dash, meaning 1, 2, 2 dash 1 dash, what is trapped between there, between the solid line and the dotted line. Now remember, we're saying that momentum is a product of mass and velocity. Momentum is a product of mass and velocity. So what I have here, let me introduce the velocity. It will look like this. So everything, the way it is, I rewrite all the items there, and then I plant the velocity just like that. So I have density, area, displacement, then velocity. Then also displacement, because velocity is displacement over time. So if I have to make now displacement the subject, it's velocity times time. So with that in mind, I can just go back to this equation, and where there is ds, I'll put v1 dt. So I have my equation here as v1 dt. Everything else remains the same. Let's do the same for section 2. This is representing the mass times velocity. Then where there's ds2, I substitute. ds2 is v2 dt. And then substituting, that's what I have. But then I'm looking for the change in momentum. The change in momentum is supposed to be final momentum minus the initial momentum. So final momentum, this one minus the initial momentum. So that's now bringing this for the final momentum minus this one for the initial momentum. Now let's figure out some things here. When you look closely into this equation, you will notice that there is A2V2. At the same time, when you look at it, there is A1V1. These represent the discharge. Because the pipe network is the same, the rate of flow, the discharge, A1V1 is equal to A2V2. So this is common and being represented by Q. At the same time, it's the same fluid which is flowing, so density 1 and density 2 are the same. So meaning that even the density is common. Then meaning what I'll have now is V1, V2 dt and V1 dt. Then in that case, it means, rather, I'll have just dt alone because everything has gone. So meaning V2 and the dt you can see is common. So I can simply now go ahead and say V2 is what has remained here minus V1 with respect to t. So I can have the t now outside the brackets. So that is where we are saying this is the same density. So density remains there. Then as if that's not enough, we've just taken a step because the density is common, we factorized. Here we have our density. But we also said these are the same. So if they are the same, then what I have is this, that the discharge, the rate of flow is A1V1, which is A2V2. Then also, it means the discharge can come out. dt is also common. So dt can be outside, then the rest of them inside the brackets. And in front, I have density multiplied by the rate of flow. Then I can put this back on the other side. We're talking about the change in momentum being equal to the impulse. So then, because you can see the t here and the t there, why not divide through by the t, and even this side also by the t? Then this will cancel out, and what I will remain with is the expression for the force. Then F is equal to density discharge by the change in velocity. But we also have density. Specific weight, first of all, is density times gravity. So if I make density the subject, I'll say specific weight divided by acceleration due to gravity. Then it means where there is density, I'll substitute with what I've just established there. Going ahead, I also have now this. If now I consider the two sections where we have angles θ1 and θ2, then I'll have two components of the force. There will be F in the x-axis, the component for the horizontal, and also the vertical component of the force. So for the horizontal component, it's just the angle cos theta. So I have cos θ2 introduced in front of, or in addition to the velocities that are there. So I have V2 cos θ2 minus V1 cos θ1. The same thing for y, but in this case, where there's cos, I'll put sine. But this is not complete. I have the effect of pressure needs to be taken care of because this is just changing momentum. Pressure multiplied by area gives us another force. So there we have P1 A1 cos theta minus P2 A2 cos theta. Then this gives us also something similar to what we have in there. The difference for the resultant coming from how the forces will behave as a result of pressure inside the fluid. So for the X component, for the horizontal component, we will say we put cos theta. When we talk about the vertical component or the one in the y-axis, where there is cos, we put sine. But this is not enough. We will need to bring them together to get one resultant force F. And you want to do this using Pythagoras theorem because this Fy and Fx meet together at right angles. So the resultant now is a combination like that using Pythagoras theorem. Then the angle of this resultant, the direction, is now tan theta is Fy over Fx, meaning that your theta is tan inverse of this ratio Fy over Fx. So this, whenever you need now to find the direction of this resultant force, you introduce theta, the angle. Let's look at the example. We have an example here. In this example, the air duct has turned through 45 degrees as a bend. Then the areas are 1 square meter and 0.5. And also in the first section, 10 meters per second is the velocity. And also at the pressure 30 kilonewtons per square meter. Specific weight has been given 11.6. So let's find the force and the direction. Now, we need first of all to get the data. First, the area that we have is 1 square meter, area 1. Section 2, the area is 0.5 square meters. The first section, which is 1 square meter, is the velocity is flowing at 10, the fluid flowing at 10 meters per second. Pressure in the first section is 30 kilonewtons per square meter. So you convert to newtons per square meter, you simply divide, rather multiply by 1,000. So 30,000 newtons per square meter. Or you may decide to write it as 30,000 pascals. Specific weight was given directly, it's 11.6. Of course, that is our discharge. We'll get back to this soon. Then the angles, because we said it tends through 45 degrees, it means the initial was 0 and the final angle was 45. Otherwise, the two should be specified exactly. But as it is, it tends through 45, meaning it started from 0, ended up with 45. With this expression for discharge, A1V1 is equal to A2V2. Velocity 1 was provided, so we need velocity 2. If you make V2 the subject, you have A1V1 over A2. So once that has been done, we can substitute. Area 1 is 1, velocity 1 is 10, area 2 is 0.5. The answer is 20 meters per second. The discharge is area times velocity. So 10 is, this is our velocity 1. Then area 1 is 1. So 10 multiplied by 1, we get our discharge as 10 cubic meters per second. With this in mind, we can now get to our working. But we have a problem here because pressure 2 is not there. We only have pressure 1. So we still need to take it through Bernoulli's equation. This is Bernoulli's equation. V1 squared over 2g plus P1 over omega plus Z1 is equal to V2 squared over 2g plus P2 over omega plus Z2. So what do you do? This pipeline is horizontal. So the Z is the same. Z1 is equal to Z2. So it moves out. So we rewrite it like that. Then we can now start the substitution. So in the substitution, V1 is 10 squared divided by 2 times 9.81. Then P1 is 30,000 divided by our omega, which is 11.6. Velocity 2 was 20, so 20 squared divided by 2 times G. G is 9.81 plus P2 is the one we're looking for. Then omega is the same fluid, so it's 11.6. Making P2 the subject of the formula, you have 29,822.63. So now we have all the tools we need. Let's find the component for the x-axis, the horizontal component. Planting the same formula, we said specific weight times discharge over acceleration due to gravity. Inside the brackets, you have V1 cos theta 1 minus V2 cos theta 2 plus P1 A1 cos theta 1 minus P2 A2 cos theta 2. This is what I have for the x component. So we start substituting. Omega is 11.6, discharge is 10, G is 9.81. V1 is 10, theta 1 is 0. Then V1 10, so we have 10 cos 0, minus V2 is 20, then cos theta 2 is 45. Pressure 1 is 30,000, area 1 is 1, theta 1 we said is 0, minus pressure 2 we found it to be 29,822.63 times then pressure 2, sorry, times area 2 is basically 0.5, then cos theta 2 is 45. Once you've done that, our F in the X is 19,407.129 newtons. For the Y, we write the same thing, but wherever there is cos, we put sine. So omega discharge over G, then we have V1 sine theta 1 minus V2 sine theta 2 plus P1 A1 sine theta 1. So here we are even saying this is supposed to be caged in brackets. So it should be like that. Then substituting, omega is 11.6 by 10, 9.81. Everything, like we said, is the same thing we wrote here, except we are just planting sine where there was cos. Hence, our Fy becomes negative 10,711.118 newtons. What we said is that we can now combine these vectorically. We can now combine these using Pythagoras theorem, where we say the F is Fx squared plus Fy squared, everything under the root. So let's substitute. Our Fx was 19,947.129 squared, plus the other one was negative 10,711.118 squared. All these under the root, or for the sake of your calculator, make sure you use my brackets there. Use my brackets here in front and at the back there, so that everything is under the square root. So your answer becomes 22,166.75 newtons. 22,866.75. In which direction? That's now part B. Here we simply say theta equals tan inverse of Fy over Fx. So then our theta equals tan inverse of negative 10,711.118 divided by 19,407.129. So what you get now is negative 28.895. When you see an angle carrying a negative, we simply say you haven't arrived. Let's get the actual value. Tan is negative in the second and fourth quadrants. So first in the second quadrant is 180 minus 28.895. It gives us 151.1 degrees. In the fourth quadrant is 360 minus 28.895, which is 331.1 degrees. Again, just as a quick reminder, where we are getting those from is from your trigonometry, where we said this in the first quadrant, all of them are positive. Here it's only sine, which is positive. Here it's only tan, which is positive. Here it's only cos, which is positive. So that's why we said tan is therefore negative only in the second quadrant and the fourth quadrant. The second quadrant runs between 90 and 180. The fourth quadrant runs between 270 and 360. Hence, that's how we work out that one to come to our angle. Let's try another question. Now this question, sorry, it's just my gadget trying to be funny. Let me go back. Okay, so our second question is right here. So just a quick minute. Question number 2. Yes, I think I might have moved a bit fast. Yeah, okay, we're here now. Okay. So question number 2, this is what we have. In this question, you have a pipe which is moving from section 1 going to section 2. Now, when you see this nature of a pipe, it's done in such a way that on one side, the section is this large. On the other side, the section is small. On the large section, the diameter is 500 millimeters. On the small section, the diameter is 25 millimeters. And then this angle theta is 45 degrees. The fluid flowing in this pipe, we've been told the specific gravity is 0.850. So calculate the magnitude and direction of the resultant force on the bend. And having been given that this is our discharge, the rate of flow. So one thing you can observe here is that, first of all, if you check carefully, unlike the other question we didn't have both pressure 1 and pressure 2. We only had one of the pressures, but the other one we had to calculate. But in this case, pressure 1 is here, and pressure 2 is also right there, 23 kilopascals. Then unfortunately, V1 and V2 not here. So we will soon find out, we can easily get around those. Then also the discharge has been given right here. Okay, let's get to the data then with that information. So that's our question. We need to find, and remember the bend is in the horizontal plane. So we are saying there is no going up, but it's horizontal. That is useful in case the pressure hasn't been given, because that's normally affected. So then let's look at the information. So our data will start from those diameters we've been provided with. Okay, first of all, pressure 1 is 40,000 pascals, pressure 2, 23,000. Omega is 0.850. So to convert this to a specific way, to multiply by 9,810. So we get 9319.5. Area 1 is pi d squared over 4. So pi times 0.5 squared over 4. Where is the 0.5 coming from? We had 500 millimeters. If you convert it to meters, you divide that by 1,000, your answer is 0.5. So we have 19.63, 0.1963. Area 2, we say pi times 0.025 squared over 4, and it's 4.909 times 10 to the negative 4. That's our area 2. The angles, similar to what we had earlier, we're starting from 0 bending to 45 degrees. So theta 1, 0, theta 2, 45 degrees. The discharge has been given directly as 0.45 cubic meters per second. Then the formula, of course, is A1 V1, meaning that our V1 is simply discharge over area 1, which gives us 2.292. If I want to find velocity 2, I should do the same thing here. So I'll say V2 is equal to discharge over area 2. Coming from that, because this is A1 V1 is equal to A2 V2. So that divided by the area, and that's my answer, 916.684. Am I done with the data? Yes. So we can now start planting this. Let's get the horizontal component. We said for the horizontal component, we write Fx is equal to omega discharge over gravity, open brackets, V1 cos theta 1 minus V2 cos theta 2 plus pressure 1, area 1 cos theta 1 minus pressure 2, area 2 cos theta 2. Then we start planting, we substitute. Omega is 9319.5 times the discharge, which is 0.45. G is 9.81. Then I have 2.292 cos theta minus 916.684 cos 45, because theta 2 is 45. Then again, pressure 1 is 40,000 times area 1, 0.1963. Theta 1 is 0, minus 23,000, which is pressure 2, times 4.909, which is times 10 power negative 4. This is our area 2. Theta 2 is 45 degrees. So with all that, our answer is negative 268,072.098. Then we do the same for the vertical, meaning wherever there's sign, we put cos and we do the substitution. The answer comes out as Fy is negative 277,110.693 newtons. Combining these using Pythagoras theorem, you'll find that this is what we have now. Both of them are negative, so the negative will dissolve because of the squaring part. So then our answer is 385,555.425 newtons. That is our resultant force. The question was also asking for the direction. At what angle? So theta is tan inverse of Fy over Fx, and we substitute. Our angle is 45.95 degrees. What did we say about tan? We said tan is positive in the first and third quadrant. In the third quadrant, you add the value you have in the first quadrant. So 180 plus 45, you get to 25.95. So this meaning it's either this or that angle, either this one or this one. And you have your final answer. As we practice, here's your exercise. Only 4 questions with all the answers provided. Take your time to go through them and push in the comments or reach out to me where you feel there's some clarity needed. Thank you very much. We link up in our next lesson.